Alright, so today it's Newton's Law of Universal Gravity. In the EPSB workbook, you can find this on page 246. So you can go there if you like right now. This is 7.3 in the homework book. And you can also go into my notes package and find the section in the notes. Okay, so the section in the notes follows the inclined plane, so you should be able to find that easily. So Newton's law of universal gravity. The equation Fg equals to mg. This one here we've been working with for a while. That's the formula for weight. Okay, it's only valid when you know the value of g. So like when you're on planet Earth, you know that value. Okay, so like on planet Earth, you know that g is 9.8 meters per second squared down, and any two objects in the universe experience a gravitational force. This bullet here is probably something that might be new to you. This was actually derived by Newton 450 years ago, which is absolutely just wild. And what we can do here is just draw a picture. So this might seem like a new idea to you, but probably not. Now the Earth is going to orbit around the Sun. Why is the Earth attracted to the Sun? Well, there's a force due to gravity. The Earth is attracted to the Sun, and the Sun is attracted to the Earth. So what this means is essentially any two objects, if they have mass, there will be a gravitational force between them. Now, the Sun and the Earth are extremely massive. They are huge in terms of kilogram, in terms of their mass. So if you put, for example, an apple next to, I don't know, a book, like the gravitational force between them is so small because they have basically no mass relative to like the Sun and the Earth. The force is so small that you don't notice it. It's just not big enough for it to be noticeable. So the gravitational force, Fg, this is really only noticeable when you have extremely large mass. This is the formula for it. This is the universal law of gravity derived by Newton, where the force due to gravity is equal to some constant, g, multiplied by this ratio m1, m2 over r squared. Okay, so g is just a constant that you can put into the calculator right here. Mass 1 and mass 2 are the objects that are experiencing the force between them. And r is the separation between the masses. So just this, make a note that this r is not the radius. Okay, it's not a great letter chosen because it can be a little bit confusing. But r is not the radius. Let me draw this for you. So here is object 1. Let's call that mass 1. Let's call this object 2. Let's call this mass 2. So what you'd want to measure from the center of the mass is the distance between the two objects, and then we would call that r. R is the distance between the center of these two objects. Alright, let's keep rolling. Force, of course, will be in newtons. The two masses will be in, so these are in kilograms. They're always in kilograms. And then the separation has to be in meters, so standard units apply. Okay, so this example here about Mike and his aardvark, you can look at the two masses. Like here's Mike, and here's his pet. I'm just going to draw a box. The gravitational force between these two things is going to be so small because, I mean, it's not a great diagram, but because their masses are so small, this gravitational force between them is going to be minute. It's going to be tiny. I guess you would draw the force vectors from center to center. So this FG like this, FG like this. And the distance between them would be R. I don't want to like make this overly difficult because it's really not that hard. To find the force of gravity between them, all we have to do is go G multiplied by M1, M2 over R squared. Now before we do that, I'm just going to help you, give you a little calculator shortcut. Alright, so on your calculator, what you can do is you can type in the gravitational constant into your calculator. So do this with me, 6.67. And then we need times 10 too, so second comma, times 10 too. And then we're going to put in the negative 11. So hit enter. And then what you can do here is you're going to hit this store button, STO. You're going to hit store. And that's going to take the previous answer and store that. And we're going to hit alpha G. So now what I can do is just hit alpha G, and it has that value stored in it. So let's do that one more time for you. So reset my calculator, and I'll do that one more time for you. So 6.67 times 10 to the negative 11. Hit enter, and then hit the store button, and then hit alpha G. And then hit enter. Alright, so now for this first question about Mike and his aardvark, you can go alpha G multiplied by the two masses, 60 times 15, divided by the distance between them squared, which is 2.5 meters apart, squared. Okay, and then you get this answer here, 9.6 times 10 to the negative 9. So we got 9.6 times 10 to the negative 9 newtons. Now I just want you to think about how small this number is. This is ridiculously small. It would be 0.000000000 1, 2, 3, 8, 9, 0. I think maybe that is even a 9. Anyways, 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah. Anyways, doesn't really matter exactly where that is, but you see, like, look how small that is. That is so small that it's actually you would never even notice it. Okay? And in fact, we don't in our everyday experience. We don't notice this. But when you have really massive objects like the Earth and the Sun, it is noticeable. So any two objects, if they have mass, there'll be a gravitational force between them. Okay, let's take a look at the next one. Gravitational force between two objects. The gravitational force between two objects of equal mass is given when the objects are separated by this distance. Determine each object's mass. So because each mass is the same, when you go to solve for the mass, what you're going to do is you're going to put them together because it's the same thing. So m1 times m2 is the exact, let's just call it m squared. Let's just call them m. Okay, so m times m, obviously m squared. So plug in what you know. Fg is 3.5 times 10 to the negative 9. G is a constant, and R is 3.5. All right, to solve this, we're going to have to cross multiply. Cross multiply divide, so 3.5 meters comes up here. That gets rid of this. And then divide by G, that gets rid of this. And then the last step is to square root all that. That gets rid of the square. And if you can't see this screen very well, turn out the lights. Alright, so here we go. 3.5 times 3.5 times 10 to the negative 9 divided by alpha G. Oh, that makes life so much easier when it's plugged in like that. Square root answer, and we got 13.5. Okay, we got two significant digits, so I'm going to round that up. And we get m is 14 kilograms. Yeah, 13.55 rounds up to 14. Okay, if two objects, each with mass m, are separated by a distance d, what equation represents the force of gravity between them? Fg will equal the constant, capital G. This is the universal gravitational constant, G. It's on the data sheet if you need to type it in manually. Now each mass is mass m, so you have mass 1 times mass 2. Well, they're the same masses, so m times m. And then we divide by the distance between them squared. Simplify this just a little bit, and we get basically m squared over d squared multiplied by that constant G. Yeah, not too bad, not too bad. Moving on. If one of the masses is increased by 2m, how many times greater will the new force of gravity be? So let me just copy and paste this to the next slide. Fg equals g m squared over d squared. Alright, so to do this type of question, we've done it a little bit before in the past. You probably don't really remember, but what we're going to do is we're going to call this new force Fg prime. And I'll represent that with a tick, a little tick on the top. So Fg prime is going to be the exact same equation, except we're going to replace m with 2m, because, oh, it says only one of the masses. Oh, that's silly. So that does not help us. Let's go ahead and back this up. And I'm just going to change this m squared to gm times m over d squared, because we're only going to replace one of the masses. So one of the masses is going to get doubled, basically. And then what's this going to how is this going to affect the force of gravity? So we'll call the new force of gravity Fg prime. And we just have to replace one of them. So I'm going to replace m with 2m. So what we can do is basically just slide that 2 way out to the front, and then we'll have g m over d squared. And gmm over d squared is exactly the formula that we started with. That's Fg. So we can replace that with Fg. All this shows is that the new force of gravity, Fg prime, is just going to be twice as large as the old force of gravity. Okay, so the new force of gravity is twice as large as Fg. So basically you can conclude that if you double the mass, let's be clear on that. If you double one mass, you double the force. We have talked about that in the past. That's called proportional reasoning. That's called directly proportional. Okay, so if you double a mass, you'll double the force. Now let's try this next one. If both masses are m, but the separation is doubled, how many times greater will the new force be? Okay, so let's just start from scratch. Fg equals g m times m, because they're the same mass, they have the same letter, divided by the distance between them squared. So that is the regular formula. And now what we have to do is double the separation. So what we're going to do is we're going to replace d with twice d, because it's going to be twice as far apart. Now I just want you to think about this for a second. If you were farther apart, if let's say the moon and the earth were actually farther apart, what would you expect the force of gravity to do? Would you expect the force to go up, or would you expect the force to go down? I mean, if you're getting farther and farther from the object, what do you think is going to happen? And that prediction we can verify algebraically. So again, we're going to do Fg prime with a little tick just to indicate that it's a new force. And we're going to go g m times m divided by, we've got to replace d with 2d, so we're going to go 2d squared. And it's important that you understand that we replace d with 2d, so using brackets will help you, using brackets. Okay, now we do a little bit of simplification. Gm times m over 2d squared is 4d squared. So all 2d in brackets squared is 4d squared. Now we just slide the 1/4 out to the front. And we can see here that that's just the original formula that we started with. Gmm over d squared. So we can sub Fg into there. Alright, so here's the conclusion. The new force of gravity, Fg prime, after doubling the distance between the objects, is going to be 1/4 the size of the original force. 1/4 the size of the original force. And we can summarize that here. If you double the distance, it's 1/4 the force. Alright, if you double the distance, you 1/4 the force. So like, what would happen if you tripled the distance? If you tripled the distance, the force would be 1/9. if you go back to the original formula, so flip back a few slides, you can see right here, so go back a few slides where it has this equation, and you can see that the force of gravity is directly proportional to the masses. So if you double one mass, you double the force. But the force of gravity is indirectly proportional to the radius squared. So if you double the radius, you 1/4 the force. If you triple the radius, or pardon me, not the radius, the distance, if you triple the distance, it's 1/9. Now try to think of it the other way. What if you halved the distance between two objects, made the objects get closer together? If you halved the distance, you would actually multiply the force by 4. If you cut the distance by half, the force of gravity would actually increase by a factor of 4. All right, let's go back to some of these problems. Now see if we can do this one quickly. One mass is tripled and the separation is doubled. Okay, so let's just use the formula that we were given at the beginning. Gm1, Gm2 over r squared. Start an Fg prime. This is going to be a new expression based on what's happening. So one mass is tripled. So I'll change m1 to 3m1. m2 is left alone, and then the separation is doubled. So r becomes twice r. How many times greater will the new force be? So what we have to do is we have to slide out these coefficients. So the 3 can slide out to the front and the top. And then ask yourself what's going to slide out on the bottom. Because you have a 2 squared. 2 squared is, yes, 4. And then r squared remains the same. This right here is the original force. So it's 3/4 the original force. Right? This was the original force. Now, how many times greater will the new, well, I don't think it's going to be greater. So it's not a good word there. It's actually less. The force is less. The mass is tripled. Okay, so if the mass is tripled, it's becoming bigger, so you'd expect the gravitational force to go up. But because the separation is doubled, they're getting farther apart. That sort of just like dominates, and the force actually decreases. It's 3/4 of the original force. I think that might be a good place to stop. Yeah, we'll stop there, and I will give you your homework for today's class. Okay, the homework for today's class will be page 246, and you're going to be doing numbers 1 to 9. Okay, good luck.